Good morning, ladies and gentlemen. So today we are going to be talking about periodic trends and atomic size and electronegativity. So a trend is nothing more than a trend is nothing more than a pattern. So we're going to be looking for patterns on this periodic table, and we'll be talking about atomic size, which is how big an atom is, and we'll be talking about electronegativity, which is how tightly an atom is able to hold on to its electrons. So electronegativity, I'm going to be abbreviating with an En. So whenever I say En, it's electronegativity. And then atomic size, I'm just going to refer to it as size. The atomic size is basically the size of the atom. But let's get started today with a little review of what we did last class. So this question says, draw the Lewis structure for the following elements and their MCIs. Now remember, an MCI is the most common ion. So what we want to do is, let's start off by taking a look at bromine. So let's draw the Lewis structure for bromine. So bromine is located right over here. All right. So bromine is element 35. And to draw the Lewis structure, remember, we want to know what the valence electrons are for the Lewis structure. So the bromine is going to be Br, and then we want to be able to draw in the electrons, and we want to draw the valence electrons. And bromine has how many valence electrons? That's right, bromine has 7 valence electrons, so we'll draw those in. 1, 2, 3, 4, 5, 6, 7. Perfect. So that's the Lewis dot structure for bromine. And now what we want to take a look at is understand, why does it have the 7 valence electrons? Well, bromine has 7 valence electrons. So right now it has 7 valence electrons. And the reason it has these 7 valence electrons is because there are 7 electrons in the outer shell. The outer shell for bromine is shell number 4. And bromine would have 1, 2, 3, 4, 5, 6, 7 electrons going across that shell. Now, it would also have all of these filled in as well. I'm not going to sit and fill them all in, but there would be 35 electrons total. But we also not only want to draw the Lewis dot structure, we also want to draw the MCI, or what would be the most common ion for bromine. Now remember, when we do most common ions, we're talking about whether an element wants to gain or lose electrons. Are we going to gain or are we going to lose electrons? Bromine, as well as all the other atoms, want to have 8 electrons in their outer shell. How many electrons does bromine currently have? Bromine currently has 7 valence electrons. So in order to get up to 8, bromine would have to gain 1 valence electron. Boom. You have to gain 1 valence electron. In order to have 8 in its outer shell as well, bromine would have to lose 7 valence electrons. Now remember, we talked about always having 8 valence electrons, and we would have 8 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. So bromine lost all of these electrons here. Bromine lost all of these electrons here. Then all of a sudden, bromine would have 8 on its outer shell. What's easier to do? We talked about it last class. Which one of those numbers is smaller? Is it going to be easier to gain 1 or to lose 7? And the answer is, it's going to be easier to gain 1, ladies and gentlemen, on this one. And so bromine would have that. So the MCI for bromine would be Br minus. So bromine would be Br minus, and there would be 8 electrons going around bromine with a minus charge, known as bromide. All right. So let's take a look at potassium. Potassium with the second one. Potassium, where's potassium located? See if you can find potassium. See if you can find potassium. There it is, element 19. All right. So if we take a look at element 19, potassium, we can see it right here. All right. That means potassium is on the 4th row, or has 4 shells. So let's start off by drawing potassium. There's potassium. And how many valence electrons does potassium have? Potassium is just going to have 1 valence electron. And this is where we come back to, are we going to gain or are we going to lose electrons? So potassium has 2 options. Potassium could either gain, let's see, so potassium is sitting here like this, right? Potassium is sitting like this with all these electrons. Potassium could gain 1, remember we skipped these in here, 2, 3, 4, 5, 6, 7. So it looks like potassium is going to have to either gain 7 electrons or potassium, which is sitting like this, could just lose that 1 electron. So what do you think is going to be easier? Do you think it's going to be easier for potassium to lose 1 electron or to gain 7 electrons? And you guessed it correctly, potassium is going to lose 1 electron. Well, potassium is sitting on 19 protons. And if potassium loses that 1 electron, that means potassium is going to be sitting on 18 electrons, which means that potassium will lose that electron there. And if potassium loses that electron, then potassium is going to have a full shell underneath. And potassium is going to have 1 extra plus charge, right? It's going to have 1 extra positive. So potassium, its MCI is going to be +1. And that would be 1, 2, 3, 4, 5, 6, 7, 8. And that would be the Lewis dot structure, right? For the MCI for potassium, all right? The regular potassium. And this would be the MCI for potassium ion. So now we're going to move on after that little review. So now what we're going to be talking about is whether or how you can tell which atoms are bigger than other atoms. So if we're looking at our periodic table, some of these atoms are big, some of them are small. And we're going to look at the trends that will tell us which atoms are larger and which atoms are smaller. Now, the first general rule to determine whether one atom is bigger than another is to look at the number of shells. So let's just take a gander and say, all right, so we have an atom, and let's say we have an atom that has 2 shells, and then we have another atom that has 7 shells, or 6 shells, or any number of shells bigger. Now here's my question. Remember, these are all scattered with electrons. Which one of these atoms do you think is going to be bigger? Do you think the bigger atom is going to be an atom like lithium that only has 2 shells, or cesium that maybe has, I don't know, what did I draw? 1, 2, 3, 4, 5. Let's draw a 6th one just so it works. Which one do you think is going to be bigger? Lithium or cesium? Well, if you just take a look at the pictures, you can see that if something has 6 shells, it's going to be much bigger than something that has 2 shells. So the first rule for drawing an atom is the more shells, the bigger, right? The more shells, the bigger. And there's really no comparison to that. There's no way to argue that one. So if we were going to take a quick look, if we were going to compare chromium and tungsten, which one would we say is bigger? Yes, tungsten. If we were going to compare phosphorus with bismuth, which one would we say is smaller? Which one would be smaller? Yes, phosphorus would be smaller. If we were going to compare calcium on row, I should probably erase these other ones. Let me change the color so we can see now that we know what we're talking about. If we were going to compare calcium on row number 4 with boron on row number 2, which one would you say is going to be smaller? Smaller. Perfect. It's going to be boron. It's going to be smaller because boron only has these 2 shells, and calcium is way over here on shell 4. So boron would have 2 shells, and calcium would have 1, 2, 3, 4 shells. All right. Well done. Mr. Bevick, are they all that easy? You know, relatively they are. The next thing that we have to learn about is how an atom is set up. We'll remember, because we've learned this before, we have a bunch of protons, right? We'll call those protons in the center of our atom. And going around the outside, we have these things called electrons. The protons are like these magnets, right? So protons are like magnets. And if you remember what a magnet can do, magnets can pull in on things. So you take two magnets and a piece of metal, and the piece of metal is attracted. So you have this protons in the middle, the nucleus, are going to pull on the electrons. So let's say that you have 5 protons versus 1 proton. Which one do you think would be able to pull these electrons in closer? Do you think the 1 proton would be stronger to pull in the electrons? Or do you think having 5 protons would pull in the electrons? And the answer is 5. That is correct. The 5 protons are going to pull much stronger on the electrons than the single proton. Because, I mean, think about it. What would pull stronger? A magnet with a power of 5 or a magnet with a power of 1? So how does that work? Well, if you take a look, we want to look at the number of protons. So let's look at lithium versus beryllium. Lithium, I'm just going to put lithium here and beryllium here. Okay. So lithium has 3 protons in the middle. 3 protons in the middle. Beryllium has 4 protons in the middle. And here's your electrons out here. Which one of those do you think will be able to pull in the electrons closer? Which one will be able to pull in the electrons closer? The magnet that has a power of 4 or the magnet that has a power of 3? You're correct. The magnet that has a power of 4 is going to pull the electrons in really close, while the electron with a power of 3 is going to leave them a little bit bigger. So let's try another one. Let's try boron versus fluorine. Let's try boron versus fluorine. Boron has 5 protons, and fluorine has 9 protons. So we'll make this one fluorine, an F. We'll make this one boron, a 5. And what atom do you think can pull the electrons in closer? The one that has the magnets with a power of 9, or the one that has magnets with the power of 5? Which do you think will be able to pull the electrons in closer and make a smaller atom? So which would be able to pull the electrons in closer and make a smaller atom? The 9 or the 5? Okay, good. The 9 is going to be able to pull in the electrons really close, while the 5 aren't going to have as much strength to pull the electrons in. The electrons are going to be pulled in really close for the 9, and then the 5 can't pull the electrons in as closely. Now, we just learned 2 general trends by doing this. We just learned that as you go across the periodic table, doesn't matter, I'm going this way. As you go across the periodic table in this direction, the atoms are going to get bigger, larger. And as you go down the periodic table, the atoms are going to get bigger. And this is the trend for atomic size. So you could look and be like, well, I can determine right now which element would be the biggest element. It would be the element that is furthest to the left, maybe lithium, but also furthest down. So francium right here is going to be the very biggest element. Now, the opposite of biggest element would be the smallest. Where on the periodic table do you think you would find the smallest elements? Well, if the biggest ones are over on the left and down at the bottom, that's right. The smallest elements are going to be over here. These are the smallest elements on this side. All right. So let's do a couple of examples and work our way through. Again, the trend, ladies and gentlemen, is going to be, as you move across, they're going to get bigger. As you move down, they're going to get bigger. Okay. So that's the trend. And you can just follow that trend. So let's take a look. The first thing is the number of shells. The second piece of information you need to talk about is the protons. So let's take a quick look here. Which is going to be smaller, beryllium or barium? So here's beryllium, and here's barium. And the question is, which is smaller? Well, let's just draw out our shells. Beryllium has 2 shells. So here's beryllium. Beryllium has 2 shells, and there's our electrons in the shells. Barium is way down at the bottom. Barium is going to have 1, 2, 3, 4, 5, 6. Each one of those would have electrons. Each shell has electrons in it. So which one of those would you say is smaller? Beryllium or barium? That's right. Barium is going to be smaller. And now let's take a look at the next one, phosphorus or sulfur. So what do we think is going to be smaller? Do we think phosphorus, which is right here, or sulfur, which is right here? Now notice they're both on the same shell. So if we take a look, we have phosphorus and we have sulfur. Phosphorus has 3 shells. Sulfur also has 3 shells. So we can't use the shells to determine which one is bigger or smaller, right? So what was the next piece of evidence we need? We need to figure out the number of protons. Phosphorus has 15 protons sitting in the middle. Let me erase that. We'll put it right in the middle so we can see it. All right. So phosphorus has 15 protons sitting, looking at all those electrons. Sulfur has 16 protons, right? This was sulfur and this was phosphorus. Which will be able to pull the electrons in closer? So what has a bigger magnet on the inside? Yes, sulfur has a bigger magnet on the inside, which means sulfur is going to be able to pull the electrons in much closer, and phosphorus is going to be much bigger, okay? So let's take a look at some more examples, shall we? Again, the trend, as you go across to the left, you get bigger, and down, you get bigger, all right? If your brain works better where you're like, I think smaller is an easy way to go, then think about it in terms of smallness, all right? We just talked about the trend on the periodic table, and that trend, again, is going to be as you move across the left, you get bigger, and as you move down, you get bigger. So this francium down here is the largest element on the periodic table. So let's take a look at figuring out which of these elements are in order from smallest to largest. So we want to find the smallest elements first. So first, let's find them. So there's lithium. Okay, there's fluorine over on the upper right. Here's yttrium. All right, and cesium. So here, ladies and gentlemen, are the elements. And we want to say which one is smallest. Well, which one is going to be the smallest element? It's going to be the one with the lowest shell. But you'll see we have 2 that have the lowest shell. So we have lithium and fluorine. And we have to think and say, which one's going to be smaller? They're both on the same shell. So now we have to say, well, which one has more protons, more magnets on the inside? Fluorine has more magnets. So fluorine is going to be the smallest. So fluorine is going to be the smallest, right? And then what would be the next biggest one? Well, the row shell 2 would be lithium. That's the little alligator mouth. And then the next one here, what would you say is going to be the next bigger element, right? Would you say that yttrium or cesium? Cesium is going to be the very biggest one, so we're going to put this one here. Yttrium, and then cesium. So that would be the order of this set right here, all right? So let's take a look at the next one. If you want, you can pause your video and work that one out. If you want to pause your video, feel free. Okay, good. So now let's take a look at the next one. We want to organize these in order from smallest to largest, which means the smallest will be over on the left. So let's take a look. Well, we're looking around. Which one has the least number of rows? Hydrogen. Notice this is at the very top. Least number of rows. So hydrogen would be next. Excuse me, kids. Let me pause this very quickly. Okay, so if we come back on in, so we talked about hydrogen. It's on the first row, so it's going to be the smallest. And then what would come next? Well, oxygen, that's on row 2 or shell 2. So that has 2 shells. And so then oxygen would be next. And then what do we have next? On the third, well, nothing on the third. On the fourth shell, we have 2. So it looks like we have bromine and copper. So bromine or copper, well, they're both on the same shell. So now what do we do? Now we have to look at the number of protons. So which one has more protons? Well, bromine has more protons at 35, which means bromine is going to be able to pull the electrons in closer. So bromine is going to be the smallest, and we're going in order from smallest to biggest. So then bromine would come next. And then after bromine would come copper. And finally, wow, this is definitely the biggest, would be radium. Okay, and so that's how we would work those out, ladies and gentlemen. All right, so that would be atomic size. Now, the next thing we're going to do, which is electronegativity, should go very quickly. It completely and directly correlates to atomic size. So the next thing that we're going to be talking about is electronegativity. So electronegativity, ladies and gentlemen, is how tightly that an element or an atom holds on to electrons, okay? So it's how tightly an element can hold on to electrons. So I'm going to draw 2 quick examples for you to kind of show this to you. Number 1 would be an example if you do have something like a lithium, and lithium only has 2 shells here. There we go. And then we take something else, like we'll take a I don't know, barium down here. So we'll take barium and I'll draw it right here. And barium's got 6 shells. 1, 2, 3, 4, 5, 6. And there's all these electrons, right? So we'll just say there are these little electrons hanging out here. There's the electrons in barium. And then here are the electrons on the outer shell in lithium, right? Do you think, ladies and gentlemen, that that's not a very good picture of I just did not do a very good job? There are the electrons in lithium on the outer shell. Do you think it's going to be easier for barium to hold on the electrons that are really far away? Or do you think it's going to be easier for lithium to hold on to the electrons because they're not so far away? Now, let's just say that I was walking down the street and I have my wallet. And as I'm walking down the street, I just have my wallet out here and I'm walking around and my wallet's just sitting way out here away from my body. Or let's just say that I'm walking down the street and I'm holding my wallet really close to me. Now, where do you think it would be easier to steal my wallet? I think it'd be easier to steal my wallet if I'm just holding it way out here, or easier if I'm holding it really close? Well, it's going to be more difficult if I'm holding it close to me. If I'm making myself smaller, I'm going to be able to hold on to the wallet better. Whereas if I'm holding out here, I'm not holding onto it as tightly. And the exact same trend happens for electronegativity. The smaller the atom, the easier it's going to be to hold on to that outer electron. Whereas this giant barium is so big, it's going to be very difficult to hold on to that outer electron. So we're going to do some examples. All right, so we just talked about the general trend, right, of it's going to be easier to, where it's going to be easier to take an electron or keep an electron. So what I've done is I have changed the trend, right? I'm saying that it's exactly the same. Nothing's changed. I'm just changing the way the perspective is. I'm saying that as we move across the periodic table, we're getting smaller. And as we move down the periodic table, wow, we're going to get bigger, ladies and gentlemen. All right. So which element is more electronegative? Sodium or lithium? So let's just take a quick look at sodium or lithium. So here's sodium. Oh, there's lithium, sorry. And there's sodium. So let's look at them. So we have sodium, which has 3 shells, and we have lithium that has 2 shells. And if you think about that, you have sodium out here in A, and it's got its electrons way out here. And then lithium has its electrons right here. Which one of those do you think would be easier? This one has 3 shells to hold on to the electrons. Lithium only has 2 shells to hold on to the electron. Well, it's going to be much, it's the one that's more electronegative is going to be lithium, because lithium is much smaller, and it's going to be much easier for lithium to hold on to its electrons. So lithium is going to be more electronegative because lithium is going to be able to hold on to its electrons better. So that's what electronegative means, how tightly an atom can hold on to electrons. So let's take a look at the next example. All right, the first one dealt with shells. And now we can also take a look at, very quickly on this one as well, which one was smaller? What's smaller, lithium or sodium? Well, this would be sodium, the atom, and this would be lithium, the atom. And the electrons are closer, smaller, holding on better. So let's take a look at fluorine or beryllium. Now, fluorine and beryllium, if we take a look right here, fluorine and beryllium are on the same shell. There's fluorine and there's beryllium. Okay? So we have fluorine and beryllium. So which is more electronegative? Which is going to hold on to its electrons better? Well, remember, the smaller the atom, the better it's going to hold on to the electron. So which electron or which atom is smaller? They're both on the second shell. So they both have 2 shells, right? They both have 2 shells. So what's going to be the difference maker? Which one holds on? Fluorine has 9 protons, right? And this one, beryllium, only has 4 protons. And remember the rules. First thing is look at the shells. And then if the shells are the same, then you have to look at the number of protons. So which one is gonna be smaller? The atom that's gonna be smaller, let's see. Fluorine is sitting on 9 protons and 2 shells, right? And beryllium is sitting on 4 protons and 2 shells with the electrons. So which has a bigger magnet? Which is going to pull the electrons in closer? The beryllium or the fluorine? And the fluorine will pull the electrons in closer. The electrons are going to be in closer to the center, which means fluorine is smaller. Fluorine is going to be more electronegative. Okay, so the same idea as size. The smaller, the better it's going to be electronegative. It's going to be more electronegative, more able to hold on to its electrons. Let's look at nitrogen on this one versus sulfur. We'll look at the purple. So we have nitrogen versus sulfur. Are they on the same shell? I mean, these just start getting super obvious. And it's like, nope, nitrogen has 2 shells. Sulfur has 3 shells. So which one is going to be smaller? Nitrogen, which has 2 shells, or sulfur, which is going to have 3 shells. Sulfur's electron is way out there. Nitrogen's electron is right there. Nitrogen's is going to be smaller. Nitrogen is going to be able to hold on to its electron much easier than sulfur. Nitrogen is more electronegative. So what trend do we notice, ladies and gentlemen? What trend do we notice? Well, as we move, so I'm going to get rid of this right here. So as we move, so the pattern, I just put this in for us. As we move across the periodic table, we are more electronegative. The atoms are more apt to hold on their electrons. As you move down the periodic table, the atom is less able to hold on to the electrons because the atom's so much bigger. And if you look at the size, you can see that as we go this way, you get smaller. And smaller means we can hold on to our electrons better. So smaller over here would mean more electronegative. And down here is going to be larger. And the larger we have, it's going to be less electronegative. So what would be the most electronegative element on the periodic table? I'll put that up here. The most electronegative, the ones that hold onto the electrons the best, are going to be up here in this area. And the ones that hold onto their electrons the least is going to be down here. So francium is the worst electronegative, the least electronegative. It's the worst at holding onto electrons, whereas fluorine is the best with electronegativity because it's one of the smallest atoms. So let's take a quick look and let's go over and let's do one more example for us. All right, so let's organize these from least to greatest electronegativity. And if we take a look at the trend, we'll be able to say, oh yeah, let's just follow the trend. That makes total sense. So again, as we move across the periodic table, right, greater electronegativity. As we move down, less. So iron, oxygen, chlorine, and bromine. So here's iron, oxygen, chlorine, and bromine. So if we just follow electronegativity, which is related to size, if we can figure out which ones are smallest, we can figure out which ones are greatest on electronegativity. So we want to go from least to greatest electronegativity. So the least electronegativity are going to be over here. So what would be the least electronegative? So the least would be the ones furthest down here. So these are least. So are there any that are furthest down? Nope, we're going to start right here at shell 4 and 5. So which one would you say is least electronegative? Iron or bromine? Well, the smaller they are, the better they are. And these are the smallest. So iron is going to be the least electronegative, followed by bromine, because it's on shell 4 as well. And then chlorine is going to be on shell number 3, which means it's the next smallest, which means it's going to have the next greatest amount of electronegativity, chlorine. And then finally, oxygen, which is like the second or third most electronegative element on the periodic table. Then this one, if you want to pause your computer, you can pause your computer and try that one on. So now if we take a look at the next question, this one says from least to greatest. So the ones that are greatest electronegativity, least over here, over there. So let's see it. We've got yttrium, right? We've got phosphorus, nitrogen, chlorine, then fluorine. So let's take a look. So we have yttrium. So which is least? Well, yttrium's the biggest element, which is down here, which means it's not going to be able to hold on to its electrons very well. So here we have yttrium, right? So what comes next? Well, we have phosphorus and chlorine on the same shell. Which will be able to hold on to its electrons better? Depends on which is smaller. You have phosphorus that has 15 protons on its shell, 2 shells. Then you have chlorine, which has 17 electrons, right? So you have chlorine, which has 17 electrons, 17 protons, I mean, and 2 shells. So which one would be smaller? Well, the one with the most protons is the smallest. So chlorine is going to be a smaller atom, which means more electronegative. So that means phosphorus is going to come next. Since we're still on row 3, then would come chlorine. And then we're going to follow the same trend for shell number 2, right? So you have nitrogen. So we have nitrogen and fluorine, okay, on the same shell. So then nitrogen has 7 protons. Fluorine has 9 protons. Which one is going to be able to pull the electrons in closer and hold them closer? That's smaller. That would be fluorine is going to be able to pull them in closer, which means nitrogen is less electronegative, which means that nitrogen can't hold them as easily. So the nitrogen, and then to fluorine, which happens to be the most electronegative element on the periodic table. So ladies and gentlemen, hopefully this all made sense. And if you have any questions, I'm going to be sitting right here. Please review the video. Just a quick reminder, the next things we're going to do, the next topic we're going to be covering directly correlates again to atomic size. So if you understand atomic size and you can sit here and you can say to yourself, yep, I know that the ones that are over here are the smallest. And I know the ones over here are the biggest. That, ladies and gentlemen, will explain everything to you because it's the trends that we're going to be following. Okay. I am sitting right here if you need my assistance. So feel free to pop in and ask me any questions you have. We can go into a breakout room. Just let me know. Okay. Good luck. Have a great day.